Hi students, in the second part of the semiconductor chapter, we discuss the types of semiconductors, how the p-n junction diode is formed, then working of diode in forward bias and reverse bias, and then application of semiconductors. Now, first we discuss semiconductors, types of semiconductors. Semiconductors can be classified as intrinsic semiconductor and second is extrinsic semiconductor. Extrinsic semiconductors are further classified as a p-type semiconductor, n-type semiconductor and p-type semiconductor. Intrinsic semiconductor. Semiconductor in pure form is known as intrinsic semiconductor. Example, pure germanium or pure silicon. At room temperature, number of electrons equal to the number of holes. Intrinsic semiconductor energy band diagram is shown in figure. The conduction band is there, Fermi level, or which is in energy in electron volt, then valence band. Extrinsic semiconductor. When we add an impurity to pure semiconductor to increase the charge carriers, then it becomes an extrinsic semiconductor. In extrinsic semiconductor, without breaking the covalent bond, we can increase the charge carriers. Comparison of semiconductors means we are going to compare between intrinsic semiconductor and extrinsic semiconductor. In intrinsic semiconductor, it is pure form, while in extrinsic, it is formed by adding trivalent or pentavalent impurity to a pure semiconductor. Second, holes and electrons are equal. Here, in extrinsic, number of holes are more than p-type and number of electrons are more in n-type. Third, Fermi level lies in between valence and conduction band. In extrinsic, Fermi level is less near valence band and p-type and near conduction band in n-type. Fourth, ratio of majority and minority carriers are unity, while in extrinsic semiconductor, ratio of majority and minority carriers are equal. Comparison between n-type and p-type semiconductor आपण नंतर करूया. We shall discuss afterward. N-type semiconductor. First we discuss N-type semiconductor. When we add a pentavalent impurity to pure semiconductor, we get N-type semiconductor. Arsenic atom has 5 valence electron. Fifth electron is superfluous, becomes free electron and enters into the conduction band. Therefore, pentavalent impurity donates 1 electron and becomes positive donor ion. Pentavalent impurity known as donor. In p-type semiconductor, when we add a trivalent impurity to pure semiconductor, we get p-type semiconductor. Gallium atom has 3 valence electron. It makes covalent bonds with adjacent 3 electrons of silicon atom. There is deficiency of one covalent bond and creates a hole. Therefore, trivalent impurity accepts 1 electron and becomes negative accept ion. Trivalent impurity known as acceptor. Carriers in p-type semiconductor. In addition to this, some of the covalent bonds breaks out due to temperature and electron holes pair generates. Holes are majority carriers and electrons are minority carriers in p-type. P and n-type semiconductors. In p-type semiconductor, acceptor ions are there. Minority are electrons and majority are holes. While in n-type, electrons are majority carriers and minority holes. Conduction in semiconductor. Conduction is carried out by means of drip process and diffusion process. Drip process. In this drip process, electrons move from external circuit and in conduction band of semiconductor. Holes move in valence band of semiconductor. Diffusion process. Moving of electrons from higher concentration gradient to lower concentration gradient is known as diffusion process. P and n-type semiconductor just we discussed as previous. Formation of PN diode. When p-type crystal is connected to n-type crystal, then a PN diode is formed. In between these two regions, a depletion layer is there, which is called as a potential barrier. Different types of semiconductor diodes are shown in figure. You can see all these figures. Now, we discuss the p-n junction diode in forward bias. When positive terminal of external voltage is connected to the anode or P type and negative terminal of the external voltage is connected to the cathode or N type across the diode. In this case, the diode is said to be in forward bias. Depletion region between these two PN type crystals decreases and PN junction offers a low resistance path, allowing a high current to flow across the junction, which is shown in figure 14.23. Now, we discuss the working of in this case. Figure 14.24 shows the IV characteristics of forward bias diode. Initially, the current is very low and then there is a sudden rise in the current. The point at which current rises sharply is shown as a knee point in the IV characteristic curve. The corresponding voltage is called as knee voltage. It is about 0.7 volt for silicon and zero point 0.3 volt for germanium. Now we discuss diode in reverse bias. When the positive terminal of external voltage is connected to the cathode or N-type region and negative terminal of external voltage is connected to the anode, that means P region, then we can say the diode is in reverse bias. In this case, the width of depletion region increases and PN junction behaves like a high resistance. The following figure shows all these things. Practically, no current flows through it with an increase in the reverse bias voltage. However, a very small leakage current does flow through the junction, which is of the order of few microamperes. Now we discuss the IV characteristics. When the reverse bias voltage is applied to a diode is increased to sufficient large value, it causes the PN junction to overheat. The overheating of the junction results in a sudden rise in the current through the junction. This is because covalent bonds break and a large number of carriers are available for conduction. The diode thus no longer behaves like a diode. This effect is called as avalanche breakdown. The reverse bias characteristics of diode is shown in the following figure. You can see. Now we discuss static and dynamic resistance of a diode. First we discuss static resistance or DC resistance. When a PN junction diode is in forward bias, it offers a definite resistance in the circuit. This resistance is called as a static or DC resistance of a diode. The DC resistance of a diode is the ratio of DC voltage across the diode to the DC current flowing through it at a particular voltage. Therefore, Rs is equals to I V upon I. Now we discuss the dynamic or AC resistance. The dynamic resistance of a diode at a particular applied voltage is defined as Rs is equals to delta V upon delta I. The dynamic resistance of a diode depends on the operating voltage. It is the reciprocal of the slope of characteristics at that point. Figure 14.28 shows how the DC and AC resistance of a diode are found out. Advantages and disadvantages of semiconductor devices. First we discuss advantages. First, electronic properties of semiconductors can be controlled to suit our requirements. Second, they are smaller in size and light in weight. Third, they can operate at smaller voltage of the order of few millivolt and require less current of the order of microampere or milliampere, therefore consume lesser power. Fourth, almost no heating effect occurs, therefore these devices are thermally stable. Fifth, faster speed of operations due to smaller size. And last, fabrication of IC is possible. Now we discuss disadvantages. First disadvantages. They are sensitive of electrostatic charges. Second, not very useful for controlling high power. Third, they are sensitive to radiation. Fourth, they are sensitive to fluctuations in temperature. Fifth, they need controlled condition for their manufacturing. And last is, very few materials are semiconductors. Applications of semiconductors. A PN junction diode is the basic block of a number of semiconductor devices. A semiconductor devices can have more than one junction. Properties of device can be controlled by controlling the concentrations of dopants. First application is solar cell. This solar cell converts light energy into electrical energy, which is useful to produce electrically in remote areas and also for providing electricity for satellites, space probes, and space stations. Second application is photoresistor, which changes its resistance when light is incident on it. Third application is bipolar junction transistors. These are devices with two junctions and three terminals. A transistor can be PNP or NPN transistor. Conduction takes place with the holes or electrons. Many other types of transistors are designed and fabricated to suit specific requirements. They are used in almost all semiconductor devices. Fourth application is photodiode. It conducts when illuminated with light. Fifth, LED, light emitting diode, which emits light when current passes through it. Household LED lamps are similar technology. They consume less power, which are smaller in size and have longer life and are cost effective. Next application is solid state laser. It is a special type of LED. It emits lights of specific frequency. It is smaller in size and consumes less power. And last application is integrated circuit, or in short it's called as ICs. A small devices having hundreds of diodes and transistors performs the work of large number of electronic circuits. Thank you. Thus we complete our chapter.